neutrons requires only 10 joules of 100 keV particles. So there is nothing strange about making many neutrons in very energetic pinch devices. And in fact, explaining it is easy in many, many ways. And in fact, X-ray lines in plasma focus, capillary discharge, and so forth are very easy to produce from impurities because you have so much energy available. Everything that can be pumped is pumped.
This is correct, but I was very astonished to notice a coincidence between the calculation of the line by the magnetic interaction and the tape. I mean, I agree such a coincidence is not 100% accurate, and much more work is needed. But that's part of future research.
But there are other filament fusion events which look very much like cold fusion because the energies are much too low. So your point is not a very good one. This is a whole family phenomenon. We need to be aware of all of that. And my question to Jay, John Paul, would be this: can you tell us? Can you show us how the break in the filament suddenly induces these deep orbits you're talking about? I mean, is that in your poster? And can this account for the fusion rates?
It was in Hawaii. But this is a measurement by Lefty Helcom, by the way. Those German experiments are interrupted, and Lefty Helcom is dead, unfortunately. I think he died of kitchen poison. But he had looked for the coincidence of the neutron with the shape of the current. So I think those experiments should be redone. And one of the very interesting type of experiments to make would be to drill capillaries in the ceramic and redo the Lofty-Hall-Graven experiment carefully.
I'm sure that this discussion will continue, but unfortunately we've run out of time, so it can continue around the post there. Now I have the pleasure in announcing the two next events. The one for all of us is to meet at the Foyer Bruce for the conference banquet. The time arranged is 8:15 for 8:30. Then the dinner will be served promptly at 8:30. And a separate announcement which has already been made in case there's anyone here who hasn't seen it. Good morning, ladies and gentlemen. I've already allowed 5 minutes grace to cover last night, so I think we should start in fairness to the speakers. Continuing the theme of new developments, which contains, as we've already gathered, a very mixed bag of topics. Nevertheless, for the first 3 speakers this morning, we will be having presentations on sonoluminescence and related topics. As you know, Dr. Lipson has already given this talk, and Tom Frederick will be giving his poster in the 3rd slot this morning. So, without further ado, I'll introduce Jim Cleese. He is going to talk on sonoluminescence, excess energy, and hypersonic pump.
Good morning, ladies and gentlemen. I would like to thank you for inviting me to come back to ICCF-5 after I had the opportunity to attend ICCF-4 last year at Mallove. And my talk this morning originally was scheduled to be sonoluminescence, excess energy, and hypersonic pump. We did not get all of the data that we were hoping to have back from Georgia Tech and Dr. Sam Martin, so I'm not going to talk a whole lot of sonoluminescence, but kind of give you an upgrade on what has happened with us at Hydrodynamics in the last year. The organizers had asked that I speak, I'm not going to be so much technical as a lot of the other speakers, but I'm going to give you kind of an indication on where we have gone using cavitation in commercialization of the pump. It was last year that we got the idea that some of our excess energy that seems to appear might be coming from cavitation. talking with a number of you at the last convention and doing some research on this subject. Dr. Kenneth Swesley from the University of Illinois has done a number of papers, and in one of his most recent papers, Ultrasonic Applications of Chemical Processing, he states that cavitation serves as a means of concentrating the diffuse energy of sound. It is the underlying phenomenon responsible for sonochemistry and sonoluminescence. Bubble induction by cavitation produces immense local heating, high pressures, and very short lifespans. These hot spot temperatures can reach roughly 5,000 degrees C, pressures of 500 atmospheres, and heating and cooling above the 10 to the 9th Kelvin. For retrospective, within the liquid radiated by an inexpensive tabletop ultrasonic apparatus, one can create temperatures of the sun's surface, the pressure drop of the oceanic trenches, and the cooling rate of molten metal splattered onto liquid helium. I think that in itself covers a lot of the aspects of what we've been used to trying to do in the cold fusion field. For those of you that aren't familiar with what we are doing, we have taken a rotating device, which we call a hydrosonic pump, and created a cavitational field where we have bubble collapses, which we feel like are the cause and the source of our energy. Dr. Martin said at Georgia Tech, he came up with this turbulent flow, the Taylor effect of vortexes. And if you look at our poster outside, we have a small pump that shows a plastic pump outside, and as we rotate that pump, you can actually see the development of the bubbles across these vortexes at specific regions of the pump. As we spin the pump at different temperatures, the color of the water changes to a milky color, and then it actually does come up to a grayish blue tint as we bring the water temperature on up to the steam level. To give you an idea of what our system looks like, for those of you that weren't at the conference last year, this is the pump itself. It's spun by an electric motor right here. Typical feed system, much as in a boiler that feeds the pump with water. We come out of the pump into a reservoir for a separation chamber for steam and or hot water. A number of you had asked what the inside of the pump looked like. It's basically a cylindrical object that bores in it at specific angles and depths, and it's spun right now between 32 and 3,600 RPM, depending on the size of the system. We have a water inlet port on one side where water enters the system. It's agitated, causing cavitation within the pump, and it comes out the other side. One of the major concerns that everyone has talked with us about is about how we do our testing and how do we make a determination of whether we have excess energy or not. And I've been asked on a number of occasions, do you make a claim of excess energy? And I don't know if it's a claim or how you would want to characterize what we're doing, but we're presenting facts that we've collected in the form of data over the past 6 years. We first saw this phenomenon back in 1989, and it has persisted since that time. Many of you that were at the conference last year realized I invited anyone that wanted to come to our facilities, come do your own testing, get your own set of data, and from that point in time, draw your own conclusions. And I stand by that same statement today. If you're not comfortable with what we're presenting, then don't accept it as fact. Come see for yourself. Make your measurements, or we'll gladly sell you a system to test. In many cases, we've offered a loan system to test. But since the conference last year, we've had approximately 40 different people come to the plant. No one has disputed our figures that they see excess energy. The conclusion has always been the same. There must be a mistake in the way you take measurements, or there must be a mistake in the way we take measurements. So this morning I'm going to cover with you exactly how we took our measurements. Since the conference last year, we installed a computerized data collection system. This is the feed source of the water coming into the pump. The water comes out of this feed pump up and into the hydrosonic pump through just a standard 1/2-inch feed line. We've installed 6 J-type thermocouples in that line. A lot of the questions always was you getting heat from the supply pump feeding system, so we've installed the thermocouples between the supply pump and the hydrosonic pump. These thermocouples are connected to a computer that takes 100 readings per second and averages those readings over the course of the time span and integrates them and gives us an average reading. Also, as a backup for redundancy for those thermocouples, we have 2 digital thermal gauges that are in there. It's just standard little thermometers in line. We also have 2 analog dial type thermometers in that line. The flow is measured with a flow meter that is connected to the computer, and we also have an analog flow meter on the line. To make sure and determine that flow is correct, I'll show you in a moment on another sheet that we actually collect the water that has gone through the pump and weigh it. The water enters the pump then, the cavitational effect takes place, it comes out of the pump, and this drawing, depending on whether we're making steam or hot water, it once again leaves the pump, and there are 6 J-type thermocouples on the outlet side of the pump. So it's a direct in-out delta T situation between the inlet temperature and the outlet temperature of the pump. It passes through a control valve, which we have a pressure gauge on, goes to a separation tank. The separation tank also has temperature gauges and pressure gauges in it. It comes out of this tank then, and depending on whether we're testing for hot water or for steam, it either goes back to a line and down and into a barrel where it's collected and weighed, or it is condensed into another barrel that has a preset amount of water in it to begin with, so that we can make the determination of how much water is in. One of the big questions last year was, how are you taking your electrical measurements to determine exactly what the input power to the motor was and how much of that input power you were getting out. We use a Duranics demand analyze machine, which is common to the electrical industry. We also use what's called a BMI 3030 unit as a backup unit to that Duranics. It's a very sensitive unit that picks up harmonics and gives you any harmonic displacement on the line. And this year we have bought a $10,000 Lowe's torque meter and put in line so that we know the actual torque measurement that is coming from the motor directly into the shaft going into the pump. The manufacturer specifications on that torque meter was that it was good to within plus or minus 0.02% of its rating between 5,000 pounds of torque and 20,000 RPM. As a backup to that torque meter, we have gone to just a lever arm with calibrated weights so that we can calibrate the torque meter before every test run is started. We're in a situation where we're monitoring just hot water. It's a very simple application. We have water coming directly into the pump. Our pump is here. Water out of the pump is collected in a barrel and weighed. The computer's taking measurements the entire time of the test. We weigh this water to confirm about 5 different intervals during the course of the test. One of our tests would last anywhere from 20 minutes up to about an hour as far as testing procedure goes. We will take approximately 4 to 5 collections of water in just a regular 5-gallon pail. We'll weigh that water to confirm that the flow meters are being accurate during the course of the run. At the end of the run, we'll take the total weight of the water that's gone into this barrel, weigh it against the flow rate of water that has gone through the flow meter during the course of the run. At the same time, this barrel also has thermometers and digital probes in it so that we can check the water temperature that's actually in the barrel, being collected, being stirred, compare it back against the water flow rate that's coming through the pump. Because one of the concerns everybody had was, are all your J-type thermocouples actually seeing the same flow stream and you're getting an uneven flow throughout the pump? If we're in a steam situation where we're testing steam versus hot water, it's a very similar situation. Once again, the J-type thermocouples would come out of the pump, this time into a separation chamber. If there's any water or moisture in the steam, it is dropped out through a trap, collected in a separate barrel. The steam itself then is sparged into a barrel. We have a starting fluid weight in each one of these barrels that we have a specific amount of water in there to begin with. We know the temperature of that water. Then we calculate the temperature rise in the water versus the added weight of the water that went into each barrel. Compare that against the input power of the system. We've placed on the posters outside some of the data. This was a run that was done back September the 13th, and just to give you an idea of what our computer printout sheets look like, we take, as I said, we take all the input temperatures here, output temperatures here, the torque is being registered here, then the flow rate is calculated for the temperature rise versus the flow. This is BTUs as far as input, or excuse me, as far as output goes, input BTUs, and then that gives you what we call the COP, or coefficient of performance. In this particular case, showing 111% output power versus the input power. One of the things that we did not discuss during all of this presentation, and the thing that has been pointed out to us, it was pointed out the other day by a number of the speakers, is we have not taken in our calculation into account any type of radiant convection losses because of the system. Our system is a big, massive piece of steel. I can really appreciate how sensitive it is for some of you who are doing work and trying to measure milliamps and watts of power, for all the skepticism and I guess abuse that we take, because we're measuring in kilowatts per hour. The average size system, as you see here, this is one of our smaller systems. It has an output capability of 185,000 BTUs. We have systems that are actually out in the field working today that are putting out in the neighborhood of 500 to 700,000 BTUs. We recently also have changed the design of the system a little bit, and maybe some of you can help. I know one has offered help in taking a spectrograph for us. We changed the design of the system, and when I say change the design, the pattern in the rotor was bored at a different angle to accomplish a higher acoustical effect. The measured acoustics of this system range between 22 and 39 kilohertz. And we changed that and got it up to about 46 kilohertz. When we did, we had some rotor degradations. The rotors actually started to dissolve or go away, and we couldn't figure out why. Further research into some of the work that Dr. Sussler had done says that because of the high pressure and high temperature components of these isolated hotspots at the center of the collapse of this bubble, the temperatures can be reached to where you can either have actual metal melting or welding, depending on whether there's suspended particles in the water and they're being bombarded. If you look at some of our posters outside, you see it on the posters, we show the rotor housings, and there's this kind of copper-looking effect around it. And we can't figure out where that copper impregmentation went into that metal from. We don't know if it's out of the water source. We've had the water check. There doesn't appear to be enough copper in the water in solution to have got that much metal into the surrounding housing, which is 1020 carbon steel, or if actually because the rotor itself dissolved, that there was some impurities in the rotor in the form of copper, and we've had that sent off for analyzation. As you can see from the housing outside, there's copper being plated or impinged into the system as far as on the housing, and in two cases on the rotors themselves. David has just informed me we have about 5 minutes, so I know my presentation is much different from a scientific approach that's been given most of the week, so I'll open the floor up for questions for the last 3 or 4 minutes of the presentation.
analysis have you done on gases on the water or on the walls of the chamber of your model?
The only analysis that we've done so far has been on the rotor itself to see what the materials that were coming apart on the rotor were. We haven't done a gas analysis yet. Hopefully that's one of the things we plan to do in the near future. Understand, I know that all of you understand what funding is and the availability of funds to carry out your research. But we're a private company. We don't have funding available to us. We are in the process of selling the system. And I think the one thing that's going to make this science go is the fact that if you can get systems commercialized and out into the marketplace working. And it's one thing we are doing with the 9 systems we have installed is we're tracking these systems very closely on electrical consumption versus the actual poundage steam production that's being produced by the systems out in the field. And so far, on the ones that we have that really need to track because they went in to replace electric boilers, we're seeing about a 19% gain over what the electric boilers were doing.
Yes, you mentioned solar chemistry. And for those of you here who are electrochemists, there is also a developing field of solar electrochemistry, which promises I think to be quite interesting. I just wonder, I don't follow this field too closely, but my question is that what I've seen of the solar chemistry, people just make statements that, well, you synthesize something unusual. Do you know, has anybody done any energy balances on solar chemical systems?
I've seen some of the energy balances that Dr. Putterman and Dr. Barber tried to do out at Cal Poly, and they appeared to say the same things. And actually, in one of Putterman's more recent papers, he stated that simultaneous may be the underlying source for cold fusion. And that was the first time.
Yeah, I'm a bit itchy about that one.
I understand.
But there are much more well-defined systems than that in the solar chemical field, with which one ought to be able to do pretty good energy balances. You know, you have a chemical coming in, a chemical coming out. You know how much energy is required for that chemical conversion. And the question is, have people gone into these more specific chemical changes? I think with solar luminescence, it's very difficult to make an energy balance very. I think that some of the solar chemical systems should be very straightforward.
I think that's one of the things that they've stated in their papers, that it's very hard to do an energy balance because of the transient nature of the collapsing of the bubbles. The one thing that we hope to do that maybe by the time we have the next conference that I can come back and bring some true scientists with me, I would point out that in the past it's been very hard for us to try to get universities or laboratories to really become interested in what we're doing. And recently that's changed. The local utility company has monitored some of our systems, has taken the system in the Georgia Power Technology system. Georgia Tech is entering into us with a program with the help of Dr. Sam Martin. And 2 weeks ago I met with NASA, and we're entering into an agreement with NASA under the Space Act agreement. The Marshall Space Flight Center in Huntsville, Alabama is going to take a pump and do extensive research on exactly what's happening inside the pump and energy balance.
You mentioned solar luminescence in the context of Georgia Tech. What are you anticipating from Georgia Tech? What kind of analyses of it?
Dr. Martin wants to take a pump and actually measure the pressure transient differences between the top of where the chamber for the drill holes and the rotors start, and the bottom, and the difference in the relationship as it passes given points within the housing itself. Because the tolerances are very close, and some of the phenomena that we've had to happen to the pump in the past, where we've actually busted glass and cracked housing trying to look at some of the things, they've estimated that those isolated pressure spots may be as much as 4,000 to 5,000 pounds of pressure. And he's wanting to see if he can isolate that. And one of the things that I learned at the conference in Minsk is that the temperature available, the collapse of these bubbles are directly proportionate to the radius of the bubble. And if that's the case, there should be an idealistic size of bubble to create and get it to oscillate to get maximum temperature out of the system. And those are the type of things that Dr. Mark's going to work with. So.
Is there any possibility of doing meaningful computer simulations of the phenomena? Or is that just out of the question?
I understand that the rotor materials that you use are aluminum and that the housing is steel. Could you comment on the significance of the materials that you use?
I don't know if I can comment on the significance. I can tell you that as far as taking energy balances go, we seem to get the best energy balance when we use a steel or aluminum housing with an aluminum rotor at this point in time. We have built steel rotors, steel housing, we've built nylon rotors with steel housing. We're in the process of, and we built stainless steel rotors now. We don't have a lot of data on that, but we're in the process of building a nickel rotor and a stainless steel housing.
There's still a lot of questions. Could we have quick questions from Dr. Hansen, then Professor Preparata, and then Dr. Hansen first, please.
Just a short comment. Has anybody done a calculation to show you mentioned the degradation of the system, that the degradation of the system is really trivial energy-wise, or are you consuming your system? I mean, you need some balance and calculation on something like that.
The degradation of the system only occurred after we changed the frequency, and it's only occurred on 3 rotors. We've got 6 years of data where there is no degradation of the rotors. The rotors, because we felt like all along, because of the ultrasonics that was going on with the system, stay perfectly clean, perfectly smooth. There's no metal impregnation into the housing or the rotor. But when we changed it and changed the bore design of the hole and went to higher frequency, we've had some rotors and some housings that have degradation.
I would like to make a very short comment. I've tried to look into this theory of cavitation, and it seems to me that this conclusion about temperatures and pressure is based on extrapolation of thermal hydrodynamics well beyond where it can hold. In the sense that there is a limit where it can pass from thermodynamics to dynamics. And the concept of temperature has only a meaning as a statistical kind of concept. But when the velocities of collapse of the bubble exceed the mean velocities from thermodynamics, there's no temperature anymore. So I believe the interpretation, the actual interpretation, and I think I will write some paper on this, actual interpretation of the bubble collapse is essentially unfounded. And there are other mechanisms at work which have to do with the formation, the fast formation of the waters back, and therefore the relaxation of the energy of the formation back of water through the electromagnetic field. And that is perfectly in agreement with the kind of theory I was talking about.
That's why I said we were itchy.
Excuse me?
That's why I said we were itchy.
Well, I mean, I think we just have to read the papers to see that, the extrapolation of thermodynamics is ridiculous. I mean, there's no equation of state when you have a so fast transition.
No.
At some point, thermodynamics has skewed to dynamics, because that's what it is.
Juliano, that's true, but they have modeled shock waves.
But it doesn't matter. It doesn't matter.
Clear shock waves are.
Well, I mean, okay, as soon as you see that the velocity of the bubble, which comes out, exceeds the mean velocity at that temperature of the water, then it doesn't work anymore.
Juliano, I'm not disagreeing with you. What I am pointing out,
But it's
they
so
do use
Yeah, but it's
classical
so
dynamics.
Yes, but yes.
They use classical dynamics and computer
But
codes.
then
That's
they
what
have
Lawrence Livermore does.
but then they have energies. Then they have energies. Don't have temperatures.
That's right.
So they talk about a million degrees. So they're wrong. Okay. Because they have an equation of state to put things in. That's what
Have you considered nephelometry light scatter for the measurement of
But
your...
it doesn't have to be electromagnetics. Right.
You must be able to do something.
It's an adiabatic collapse.
Sorry, could we continue this, Paul, please, and give our head a chance?
Have you considered nephelometry light scatter for the measurement of the size and concentration of cavitation bubbles?
I have not, but that's one of the things that Dr. Martin mentioned, that he was going to be able to measure with something at the Georgia Tech. Allowing me to come, I'd just like to point out one thing before I leave, and I appreciate Dr. Giuliano. It's for you as scientists to figure out what's going on. It's for us as industrial salespeople to get these systems out in the field and sold.
The next paper is by Dr. Fukushima, entitled "The Stability of Bubbles Induced by Supersonic Field Sonotrusion." Dr. Fukushima.
The subject of my book is sonotrusion. I proposed sonotrusion in 1992 at an aware conference. In this book, I want to focus on compressibility of liquid and stability of spherical cavity. The idea of sonotrusion originates from the sonoluminescence phenomenon. Therefore, I would like to briefly introduce the sonoluminescence phenomenon. Supersonic field applied to a liquid induces bubbles in the liquid, and then the radius of bubbles start to oscillate almost in phase with the applied supersonic field. In the contraction phase of the bubble, the temperature of the gas within the bubble is significantly raised due to the adiabatic compression, that is formation of hot spot, and subsequent radiation of photons. The maximum temperature of the hot spot is experimentally estimated, and this is why nowadays it's widely believed maximum temperature may amount to 10 to the 5th Kelvin. The purpose of my research is to theoretically determine the upper bound of T max of the hot spot. We calculated the T max in Delos order approximation in 1992. Therefore, we have made a number of simplifying assumptions. That is incompressibility of liquid, adiabatic response of van der Waals gas content, which is van der Waals gas, and the spherical symmetry of the power. And therefore, under these assumptions, we can easily derive the Rayleigh-Peasant equation, which describes the time evolution of the radius of spherical cavity. Rho is the constant density. PL, PG is the pressure of the liquid and gas as the bubble. Sigma is the substantial. P0 is the ambient pressure of the liquid, and PA and FA are amplitude and frequency of upright supersonic field. Initial condition R0 is the initial radius of the bubble. By numerically solving this ready-to-set equation, we can get this figure. There also the approximation and supersonic field parameter is like this. And R0, T max in Kelvin versus R0 in micrometer, initial radius of the bubble. When R0 is about 10 micron, T max is order of 10 to the 7. And when R0 is 1 micron, T max is order of 10 to the 10. Very high temperature, high enough for hot period. But these values are obtained by use of the calculation. Therefore, in order to obtain the quantitatively reliable result, we have to go further into more realistic calculation. This is a list of simplified assumptions we have made. That is, we neglected the compressibility of liquid, thermal irradiation, heat conduction, mass diffusion, evaporation and condensation of vapor, phase transition, and non-adiabatic response of gas content, and further we had assumed the stability of spherical gravity. In this talk, I take into account the compressibility of liquid and examine the stability of spherical cavity. Therefore, at first, the compressibility of liquid. In this case, relativity-set equation should be replaced by Gilmore equation. This Gilmore equation. We solve this equation numerically and get this figure. Again, P max versus R0. This broken line corresponds to incompressible liquid. That is our preliminary calculation, the result of our preliminary calculation. This two solid line corresponds to compressible liquid, our new result. In the compression phase of the bubble, the gas within bubble is surely subjected to the adiabatic compression. But in expansion phase, gas can expand isothermally or adiabatically. This upper line corresponds to isothermal expansion, and this lower line corresponds to P maxes of order of 10 to the 7th. We have used this high supersonic field parameters. Therefore, the parameter dependence of P max is very important. Then next, we shall examine the parameter dependence of P max. Before going further, I want to point out this point. That is, for isotopic expansion, gas should expand as slowly as possible. That means the frequency of the applied supersonic field, FA, should be as small as possible. Now, this view graph depicts T max again, R0 again. These three lines correspond to values of this product, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3 meter per second. We see decreasing values of this product, T max, steadily increase. 10 to the 7th, 10 to the 6th, 10 to the 10 to the 7th, and 10 to the 9th. And we start the saturation, tendency of saturation, P max increases. We have assumed that isotopic expansion to calculate this value. This view graph clearly shows that small f-ray surely assures isotopic expansion, and that means simultaneously small f-ray assures the high T max. Fortunately, small f-ray assures the high T max. Small f-ray.
What is FA?
F-ray is the frequency of the supersonic field. And T max also depends on R0, the initial radius of the bubble. With increasing PA, amplitude of the applied supersonic field, 2.0, 4.0, 6, and so on. With increasing PA, T max increases, but there is a tendency of saturation. Now, let me move on to the stability of spherical cavity. This is the equation of bubble wall. This is the equation of bubble wall. RS is the distance between the bubble center and the bubble wall. Capital R is the radius of the spherical cavity, and this term describing the deviation from spherical cavity, spherical bubble. This deviation parameter A should satisfy this preset equation. We numerically solve this equation and we get this improved one. As delta is t, time t, in unit of period, in unit of the period of the supersonic peak, 0.0 to 1.0, therefore one cycle of oscillation. Radius of the spherical cavity R starts with R0 and goes up like this up to 40 times R0 and suddenly goes down to minimum value, to the minimum radius, which value is about 0.1 times R0. Deviation parameter A starts with initial value A0 and oscillates for a while and goes to 0. Become very small, take very small values. And then as the final step A increases roughly up to 2.4 times A0. In any way, deviation remains finite. Therefore, spherical cavity is stable against small deviation from the spherical cavity. I also calculated I also proved that spherical cavity is stable against the small spatial inhomogeneity of pressure. Therefore, however, it is well known that spherical cavity is unstable near the solid surface. It is well known because of the great spatial inhomogeneity of the pressure. The conclusion. But hot fusion is still possible for compressible fluid, liquid. The second point is spherical cavity is stable at the remote point from the solid surface. Okay, thank you for.
There have been, there was a paper published in Physical Letters that talks about the pressures on the liquid during bubble collapse, where you could form I7 during the final stages of the collapse because that became the thermodynamic favorable condition in the liquid because of the melting point of I7 rising smaller in temperature with pressure. Are you familiar with this? They said that would reduce the total final pressure within the collapsing bubble. During the bubble stages, it's fine.
I calculated the pressure and density of the bubble of minimum radius.
This is in the liquid. The pressure of the ice forms in the liquid wall.
Yes, the liquid wall. Yes, okay. Yes. I have used the polymer gas and therefore minimum radius and maximum density almost equal to the density of the liquid. Therefore,
play this game and get this very high temperature, this very high pressure, of course. One of the problems is, of course, with the I-7 or whatever, this very high pressure. Also, what is the reason why T is, yes, but I'm talking, all right, but I think this is important, okay? For educational purpose, okay? Not only for technical. Okay? The point is that they have a blue light emission, actually they have a spectrum emission, which is very high. So it must be temperature. But this is just predicated upon a very narrow confine, of what the physics laws are. Secondly, there's an enormous repetitivity, periodicity. Now, if you have this enormous temperature, you have enormous fluctuation, how can you have this smooth system? It's ridiculous. I mean, a physicist who has done physics all his life just revolts against this kind of interpretation because it can't be right. I mean, there is a repetition rate, there is a periodicity which is enormous, over thousands and thousands of cycles. And now you have temperature of the order 10 to the 9 Kelvin. I feel like my spine.
Okay, I calculated the one cycle of the oscillation. One cycle, only one cycle.
Yeah, but experimentally, yeah, I mean, Paderman and others have shown an enormous repetitivity. In other words, nothing changes over thousands and thousands, 100,000 cycles. And now, I would expect enormous fluctuation. What is temperature? What is it? One must be serious.
I have used a conventional physics.
Okay, well, the next, thank you very much. Next talk is by Dr. Evans of the Chemistry Department, University of Hong Kong. This is, in fact, presented as a poster with a slightly different title. A more general title is clearly fusion energy in the bubble.
I would like to thank the committee for permitting me to talk. I think after I present what I'm going to talk about, I may not want to think. So, because I've basically gone into the drink. Juliana wanted to. But the real title I had when I submitted this abstract was the biological effects of ultrasonic cavitation. Professor Fleischman said this is a cold fusion meaning. One, we have the problem with cavitation, whether that's cold fusion, and then biological seems to be far away. But the physics that I like to present is applicable to sonoluminescence, biological layer. Professor DJ mentioned or presented the proposition of cavitation related to cold fusion, and I'll let it go at that. Anyhow, if you go to the literature and ask what are the causes of the biological effect of ultrasound, what you will see currently and in the past is a high temperature causes the vapors inside to ionize and goes on to the biological effect. This is not really well understood. bequest has presented also high temperatures, but their geometry is a little different. They use the flat geometry, whereas all the others use spherical geometry. And late Julian Schwinger's idea on Casimir, he has a flat-like model too. He never got to predicting high temperatures, so I know. But despite all of this, what is widely believed and widely known, Professor Crum in Physics Today, a recent article, I'm sure all you people read it. He's hedging the best. He starts hedging at this point. The problem is that the pulse that they see in sonoluminescence is one word 50 picosecond. And the entire thermal model simulation gives you a long time. So they're already hedging it's a high temperature model. Okay, the proposed mechanism I'd like to present is probably closer to what Giuliano suggested. It's really quite basic. You don't need supercomputer, but you do need a little bit of Wien, Planck, I think the model I like to present is quantum mechanical in origin, based on described electronic state of a molecule and a negligible change in bubble gas. I think you're going to see this. I'm not sure I want to thank the committee for permitting me to talk. So anyway, if I go on, as an American, keep on. So the bubble conditions prior to collapse. What I really think is going on, you have an almost nearly evacuated bubble. You do not have any gas. What has been neglected in most of the analytical work is that during the bubble expansion, the gases achieve 10, 20 degrees Kelvin. This has been shown in the UCLA data. But no one takes into account the fact that gases will condense out. So if they condense out, you're really left with a nearly evacuated bubble. If collapse occurs, if you wait longer, of course, the effect will come back. So if the bubble collapses quickly after expansion, then the bubble could be almost evacuated. So I have two options here. The bubble is filled solely with the vapor pressure of water surrounding the ambient temperature, including trace amount of dissolved gases, and filled with external gases as atmospheric pressure bubble through. This is typically what they do when they do sonoluminescence. But both of these converge to an almost evacuated state. Scott has mentioned shock waves. Well, if what I'm saying is true, if the bubble is nearly evacuated, there are no shock waves. So we go on. The collapse geometry, what I think is going on follows from classical physics. The bubble collapse is an unstable process, and it should follow a minimum energy path. Unlike bubble expansion, which is stable, bubble collapse is unstable. So you have to find a minimum energy path. You cannot theoretically assume the bubble stays spherical. So since a spherical bubble follows the path to maximum energy, and a pancake-like shape follows minimum energy path, you get a picture like this. The characteristic dimension delta across the flat side of the bubble, and then the velocity of the water on either side is the collapse of two sides. And here you see an angle theta. Each of these molecules on the wall, if you think plane, it's emitting radiation, it's all over the place. But if you average in the manner of Rickmeyer overall angles, you get an averaging coefficient of 1/3. I'll refer to that. full visit, nothing new about it. And if the mean free path is less than the bubble radius, then the thermal state is likely. If the mean free path is greater than the bubble radius, what I call a change in the thermal state is unlikely. There's some new concepts here, but the physics is old. And then I plot here mean free path is the temperature for the water molecule. And, what you see at 20 degrees C here, the mean free path of the water molecule is 13.5 microns, and if at room temperature the bubble radius is less than 13.5 microns, then I would expect the thermal state to change in the thermal state to occur. If, however, the bubble radius if the bubble radius is greater than 13.5 microns, let's say 40 microns, then a thermal state energy change will occur. If it's less than 13.5 microns, that is, if the mean free path is greater than the bubble radius, then there really is no change in the thermal state. So photon emission is favored if the thermal state does not change. Mean free path is greater than the bubble radius. And if you look at around 0 degrees C and 20 degrees C, you see a big change in the mean free path. If you remember what Julian Schwinger did with the Catherine model, he had difficulty explaining the dramatic increase in photons as you went from 20 to 0 degrees C. And this would explain it. That is, a 40 micron radius at 20 degrees C, the thermal state would be favored. I use favored because it is probability. But at 4 degrees C, as you can see here, the UCLA guide, the mean free path and the bubble radius are about the same. So you would expect those. There's another aspect about collision-induced energy change in your liquid density. If the bubble is evacuated and the walls come together, you get collisions of the water molecules in the two walls. But I don't, for the purposes of time, I'd like to neglect this. It's not important anyhow. But the electronic excitation mechanism, if this is all true, if there's nothing in the cavity, how do you explain the photon? Well, Professor Marcus from Caltech, he was a laureate in electron exchange. I talked to him when he was in Hong Kong, and at that time I had another screwball idea, but he convinced me there's got to be energy in the cavity. So when I was thinking about it, I said, okay, what is it? The only energy that's in the cavity, it can't be in the evacuated cavity, is what Planck told us many years ago. And it's the infrared energy in the water. That's all that's there. So what I went to was Gasiorowicz. He pointed out that when he originally derived the radiation wavelength and cavity side, he did that from his authorship. And Rick Meyer has a theory for that. So what you wind up with here is just the iron energy of delta, which is the energy from the surrounding, and T is equal to H nu. And as the bubble collapses, you have to satisfy And for noble gases, which most of the sonoluminescence data show, you get a very sharp increase in photons for the noble gases. That's because all you got is photons. You don't have bonds to break to quench the energy. So, here is a quick derivation of Rick Meyer's approach, and I think for the, again, I don't have time to do it, but it's out on the board. So, the time of bubble collapse, I want to compute it. If what I'm saying is true, then the bubble collapse is within the range of the photomultiplier. There's a band on it. And UCLA band is between 230 and 600 nanometers. So if I collapse a bubble in that range, what I find, if I take the velocity of sound for water, nothing in the cavity, then I get about 60 feet of that. So, very close to the data. And then you can go through the Planck energy and radiation pressure. What you wind up, you can write the energy at any value in terms of IR energy. Okay? There you get a plot like this. I added this little line here. This is a plot of Planck energy versus bubble collapse. We mentioned delta C. Remember the individual picture of delta? Delta C is the density of water. For 1,000 kilograms per meter cubed, this is 0.31 nanometers. Delta C. So if I start off and I crash down to 0.31 nanometers, what I do, I generate the curve. You see all kinds of curves here. I guess you can read that. 200 nanometers and 10 microns. So in the IR spectra, you have some type of frequency distribution. If you're in biological surroundings opaque to UV-VIS, that is, you can't get any other energy in there than IR. What you wind up with is if you take 293 Kelvin, you have 9.86 microns at the peak of the curve. When you crash that down to liquid density, 0.31 nanometers, you get around 3.18 electron volts. And that happens to correspond to blue photon. So what Jim Briggs has seen is a blue haze and its bubbles are amazing because you're really converting IR to blue light. That's a 309 nanometers. And then from a biological point of view, that's not very interesting. What you really want is just lower, let's say 250 nanometers. And 20% of the energy at 293 Kelvin is applied. If you crash that down, you get 250. Go to GE or Philips and you want to buy a back or a side UV lamp, they'll give you one at 253 nanometers. So it's very close. So if this is true, then if I add photons, let's say blue photons to the water, and if they have a lifetime long in relation to the crash time within that water, then I can talk about higher energies. So if I, again, go to the same theory, I get around 42 electron volts in the XUV, 30 nanometers. And the UV enhanced ultrasound, the conclusions are somewhat self-evident at this time, but the UV enhanced ultrasound is what we will work after. We feel we can make this near term. That is, in Hong Kong, in China, if you have fish for dinner, if you have fish for dinner, you go to a restaurant with a fish tank, live fish, so you can pick your fish. That's their tradition, which is fine, and then they cook it for you. But there's a problem because in Hong Kong there's a lot of cholera in the water. So people are very concerned about eating fish at restaurants. So we're trying to make a device which you see out there to take the water out of the fish tank, through it, back to the fish tank. I know this is in cold fusion, but I don't think it's sonoluminescence, but but to go on, since I don't have time, we get to the have done it. And when you do that, I have criticized this design. But anyway, for this conference, I rewrote it in the format. But basically, I'm saying nothing more than what you can already read there. In effect, there is no line temperature. And you know, I also talked about what I call UV enhanced ultrasound. And again, it's the latter part of the distance. But the point I want to make here, maybe this is where cold fusion would enter in, is that usually only photons, when you do this through typical molecules, you're only going to see photons, UV, UIS photons. But cold fusion may be possible if ultrasonic cavitation could amplify IR energy to X-ray. Then there would be something at about 10 keV. But I define cold fusion as fusion that occurs because of the changing electronic state of the molecule, not the thermal state. So I'm distinguishing between thermal and electronic. In contrast, hot fusion would be fusion from the thermal state. Okay? Everyone's trying to go into the front door of hot fusion thermal state, but there's a back door. The back door is the electronic state, but what you'll see here is being very difficult. I reiterate what's on luminescent energy. I talked about the blue light, but still, blue light is only about 3 electron volts. That's hardly 10 kV. So the probability of cold fusion, that is, in the approach I'm talking about, is not very great. But if you enhance the ultrasound UV, you can improve it, but you would need about 250 simultaneous activities to do that. And with the photons, the UV photons can stay in there long enough without disappearing is another issue. So if I'm intrigued, I say conclusion, ultrasonic cavitation without UV enhancement, and the body can live more experiments, not by either hot or cold fusion. However, since molecular spacing, you're going to take an average density and you may get a couple hundred electron volts, which isn't that big. So that's really all I have.
I nearly agree with everything you say. I think it's so important that I just comment that I think some of us would appreciate it if you could have a copy of your both stuff so that we can look at it early on. I think that is, when I said that is this field of solar chemistry, I think what is fairly important, I think, to establish now whether solar chemistry is photochemistry or whether that solar biology is photobiology, or whether that is something more in the field. I think that could be established. But fusion is possible. If there are X-rays, then you will get the radiation chemistry here. And I think that the important point there is to look for the products of radiation chemistry. One knows, right, is that, the old Habermas stuff. You have to track through that. And that is chemically really fairly straightforward.
Well, in answer to that, that's very difficult, and that I really think if you look at Livermore Labs, Sandia, Los Alamos, they could do a simulation where they include the glass, the condensation, all of that can be done now. They have the facilities, they have the money, they have the people, they could do that. So that's something, Professor Fleischman, which is beyond what I can do, but I know that can be done. We're going after the biological because we see a market. And if it's related to strong tell you, most importantly, we ran tests in Hong Kong before I left. And those are bacteria tests where I took the water directly from the fish tank, much to the chagrin of the owner. He didn't want me to take the water from the tank because, quite simply, they were afraid of losing business. But anyhow, we tested that before and at 1 gallon per minute, and we eliminated everything. There was quite a bit of bacteria. And I would have brought the Petri dishes with me, but as an engineer, I was unaware of how dangerous it might be. You may start off with one bacteria after 24 hours at 130, 40 degrees C. You get billions of bacteria. If that would ever get out, so it would be illegal to take it out of the country, let alone take it out of London. So I would have liked to have brought that. It would have been very impressive.
Okay, let me mention one small point. Are you counting the viscosity of the water in your assumption? No.
I don't use the response to the water. All I say is that since there's nothing in the bubble, there's nothing to restrain the collapse. And I pick a number without tremendous computer simulation. Without tremendous computer simulation.
That's my theory.
I don't think that that's important. The issue is the basic physical concept that Giuliano keeps talking about may have been lost in all these different computers.
Would you like to comment?
Yes, I think, if I may say, that Giuliano is better suited to describe what I do.
Yes,
Additional water is very much viscosity in some kind.
you have done it very well, but if I can make a comment, yes, I agree with you also, like Martin says, almost 100%. However, I believe there's an element that is missing here, and that is, there's certainly, when the bubble expands, you certainly have a water molecule in the bubble, because that's the evaporation, and when it gets back, so now that you have the collapse, now this water molecule, what do? Because it's very fast, this collapse. Okay, they go at a certain point, they form again water, and when they form again water, in fact, there's a critical density. When the water molecules in certain region, in fact, close to the collapsing level, reach the minimum, the critical density, which is a third of the water density. Then you have a formation of this coherent of a coherent domain of bubble, and this, due to the fact that it happens very fast, this can be done due to the fact that it's exothermal. It's exothermal. There's no thermicity here, so they can only get through the radiation or through the electromagnetic field. And I calculate you can get up to 15 electron volts, which I think is perfectly okay for your E. coli. For E. coli.
I agree. Oh, yes, for the biological, this clearly works.
Can we have Dr. Cabinet?
But I presume I was in planking position.
Well, yes, but the point, I don't understand how you can. Sure, you're right, but I can understand how you can enforce your boundary conditions on a surface which is made of other molecules.
Again, the Rick Meyer approach, all the molecules on the wall are radiating different directions. It becomes coherent in the aggregation process.
But still it's thermodynamical, and here you really don't have any thermodynamics.
I think Giuliano's raising a very interesting point. I also found your talk very intriguing. It obviously identifies a limit that's an interesting one to explore. A number of questions that computers could actually address, where you do take, make it evacuated as you suggest. Certain questions, for example, are the importance of the shape, pancake shape, which you probably talked about. Other questions are the reflectivity versus absorption on the boundary condition. An interesting question, I think, is the ratio actually of the reflectivity to the absorption, and how, and perhaps you can actually model that. I don't know.
Oh, I think you can. But you see, you can always argue that probably also very, very weak because of those numbers.
Just one other quick question. You considered electronic states primarily.
Yes, only electrical.
Water is well known as protons have a high mobility of water. I was wondering whether or not some of the energy that would have to be accounted for increase kinetic energy.
Well, this theory does not predict any excess heat, right? Energy is converted from the collapsing bubble through Planck to the molecule emits the proton. Unless there's a cascading effect beyond that, it's beyond my comprehension. There is no excess heat. Well, there's no excess heat.
No, I wasn't talking about excess heat. I was talking about.
I understand what you're saying, but again, same thing. I don't know.
Okay.
I think we should thank Tom for an excellent talk. We move on now to another aspect of our topic. Paper given by Dr. Raiko Matoya of the Research Center of the University of Japan. And the title of the book is Future Products of Cold Fusion for Electrolysis in Harmony and Maritime.
Thank you, Mr. Chairman. For the last 3 years, I have done the experimental work about the cold fusion in light water to confirm the occurrence of the cold fusion and got several evidences which will be today's topics. The first is the mechanism of cold fusion due to electrolysis. Second, the result of excess heat measurement. And third, the product of cold fusion. Mainly, I will talk about the result obtained in cesium ion solution today. At first, I would like to speak about the mechanism of hydrogen evolution reaction in alkaline solution on active metals. We were studying in 30 years the kinetics of hydrogen evolution reaction. By use of carbon transient method and concluded that this reaction occurring through the following scheme. The most rapid elementary step of this reaction is the discharge of alkaline metal ion as a double layer. Now I write 1 plus, but 2 or 3 plus also available. And it forms the intermetallic compound denoted IMI. It's made with cathode material. As Dr. Clemens yesterday showed the differential curve of this amount. Here, We know from these results, intermetallic compound penetrated into about 1,000 more layers steps from electrode surface. Thus, the galvanostatic study has revealed the presence of the intermetallic compound between cathode materials and the solute cations. For example, alkali or alkaline earth cations and some others. Almost all electrochemists believe that the electron transfer step of hydrogen electrode reaction in alkaline solution is the discharge of water molecule, but it is not true if you take the active metals cathode. Taking account of this mechanism, the mechanism of the cold fusion becomes very understandable. Like this. Intermetallic compound, nuclei, reacted with another intermediate of hydrogen electrode reaction, or neutron, deuteron, tritron, or alpha particles, and made another new intermetallic compound, but nucleus another different nucleus.
And the Coulomb pattern?
I'm sorry.
Yes, after that.
These generated by the cold fusion reactions themselves. Namely, it is the chain reaction system. As you see here, I want to stress that the cold fusion in the other work can be expressed by the reaction between two intermediate of hydrogen electrode reaction and cold fusion reaction, which is occurring in the surface layer of the electrode. Platinum group metals are the most typical active electrode, and additionally nickel, titanium, silver, and gold are also included in this active hydrogen electrode. I will not speak about today the experiment of measurement of excess heat, but I want shortly to say the following. I used so-called thermal open cell so that you know very well the input power for the electrolytic cell was collected by the enthalpy change of the decomposition of water nickel. The excess heat was observed in also cesium sulfate solution on porous nickel. It was comparable with that in potassium solution, but porous nickel was easily dispersed in cesium solution. It also may indicate one of the evidence of the cold fusion. If praseodymium is formed in solid electrode as one of the nuclear products, the electrode becomes very brittle. Hence, I used platinized platinum electrode. In sodium solution, I observed no excess heat practically, but it is in this solution, tritium and sodium 24 was detected in simultaneous observation. As neutral products, the following species have been found. Tritium in the old solution investigated and calcium in potassium carbonate solution and products of cesium plus neutron and so on of light water and sodium 24. Now I will talk about the case third, because I talked about another previously. In the case of electrolysis of sodium solution, the electrolyte was analyzed by means of ICP-5 spectrometer. For this experiment, I used two kinds of electrode, platinum, and porous nickel. Cesium ion is the most appropriate reactant among alkyl metallic ions to measure the amount of products owing to 100% of natural abundance of 133 cesium, as well as sodium 23. The cathodic polarization in cesium solution caused very strong dispersion of porous nickel, as I said. The dispersion of the nickel cathode began in a few hours after starting the polarization. The porous nickel sputtered out a lot of very fine nickel powder together with very fine hydrogen bubbles from every pore on the electrode surface. Such a very strong dispersion of porous nickel due to electrolysis occurred often in cesium ion solution. The figure shows the typical mass spectra concerning the test electrolyte in the cell with platinum electrode. But here, after in platinum cell, I will say. And that in nickel cell. In the region from 130 to 140 mass number. of the increase of products in electrolyte in platinum cell. During 18 hours electrolysis, 18,000 coulomb were spent. At mass number 132 and 134, as denoted by class, these could not be determined quantitatively because the resolution of the spectra for these mass number were insufficient. Here is very big 133 peak. In this picture, I show you here. The already known reaction for nuclear production in the nuclear reactor are shown by the red line, black line, and the reaction used for activation in the nuclear reactor also are shown by broken line and such sign means natural feedback. And I add the several reactions shown by green line, which may be occurring because their spin changes were found to be less than 2, also taking count of their reaction energy and parities. On the basis of the scheme, these nuclear products were identified at each mass number shown the last table. They are shown by circle, green circle. Here is the starting nuclear. On the other hand, there is not the fusion product in nickel cell, the same range except for 132 and 138. It was this which could be determined to be 0.6 ppm, but in control solution 0.4 ppm. However, fusion products were not detected in nuclear cell. There are two possible explanations. One of it that the electricity spent for electrolysis is considerably small in comparison with that of plasma. So the heat evolution in nickel cell was vigorous. Time is not so about it. I cannot speak about it. The other is the fusion product nuclear reaction, like as in a nuclear reactor. Thank you.
Thank you, Dr. Swear. Dr. Kishimasa.
You mentioned that you mentioned that you observed sodium-24 when you used sodium carbonate solution.
Yes.
And if I'm not mistaken, sodium-24 has a 14-hour half-life emitting 2.7 MeV gamma. So did you measure when you saw the spectrum, for example, or something? That would be a very significant observation if you could measure the radioactivity of sodium.
I didn't talk about it, but I used for it the gamma ray spectra, so immediately evoluted. So after that, immediately I can observe every time. So
No, but you are able to confirm it is a 14-hour half-life?
no. You see, in gamma detector, I set the cell.
Yes, a couple of questions, Rika. Did you look for magnesium in the case of the sodium solution as a possible nuclear ash?
I'm sorry.
Magnesium in the case of the sodium solution?
Sodium solution?
Magnesium. Did you look for magnesium?
Sodium plus a proton would give you magnesium. The other thing is, was there a correlation between the excess heat you observed in these products?
Yes, it's interesting question. I didn't, I want ICCF, I don't use for it, and I am thinking now about how to do it.
Finally, experimentally, how did you sort out the different isotopes that you claimed in the cesium case? Did you use mass spectrometry?
Yes.
What kind of mass spectrometry did you use?
ICCMS.
Just a couple comments. You found excess heat in the case of sodium, and you know Mills claims that his model forbids that. And I'm just wondering, are you able to say that the impurities are low enough level that basically you could claim that the excess heat is associated with a sodium reaction?
I don't understand.
I guess I should talk to you later about this.
Yeah.